In 1969, as the Apollo program achieved its lunar landing goals, a presidential space task group looked toward the next decade. Their priorities shifted from deep space exploration to economy. NASA required a system that could provide regular, cost-effective access to low Earth orbit. This directive became the Space Transportation System. NASA developed a fleet of winged vehicles to fulfill the mandate. After atmospheric drop tests with the prototype Enterprise, the agency constructed 5 operational orbiters: Columbia, Challenger, Discovery, Atlantis, and Endeavour. This schematic outlines the orbiter's distinct anatomy. Measuring over 122 feet long, the vehicle featured a large central payload bay enclosed by operable doors and a double delta wing swept at 81 and 45 degrees to manage the intense friction of atmospheric entry. The orbiter was only one piece of the launch stack. To escape Earth's gravity, its 3 main engines relied on a massive external tank carrying liquid oxygen and hydrogen. Flanking this tank were twin solid rocket boosters, providing the majority of the initial thrust. The final design was a compromise between budget constraints and technical ambition. Instead of a fully reusable system, NASA built a partially reusable architecture that would prove to be deeply complex to maintain and operate. On April 12, 1981, astronauts John Young and Robert Crippen boarded Columbia for STS-1. For the first time, an untried, winged spaceplane was cleared for a crewed maiden voyage. During ascent, the external tank feeds liquid hydrogen and oxygen into the main engines. After maximum aerodynamic stress, at 45 kilometers, the solid rocket boosters sever and fall to the ocean. At main engine cutoff, the orbiter jettisons the empty tank to burn up. This diagram reveals the orbiter maneuvering system. Located in 2 pods on the aft fuselage, these twin engines provide the final thrust required to push the orbiter into its designated trajectory, and later to alter its path through space. STS-1 validated a radical concept in aerospace engineering. It proved an asymmetrical, winged vehicle mounted parallel to its fuel tanks could survive the extreme acoustic and structural trauma of vertical rocket ascent. Following a brief series of test flights, NASA declared the Space Transportation System operational in 1982. Through the 1980s, the shuttle took on a heavy workload, ferrying a constant stream of commercial satellites and classified military payloads into orbit. The addition of the European-built Space Lab module converted the orbiter's payload bay into a pressurized laboratory. Astronauts were now working inside a dedicated facility, conducting sustained microgravity research in astronomy, radar, and life sciences. The rapid pace of these missions came to an abrupt halt in 1986. 73 seconds after liftoff, the Space Shuttle Challenger broke apart in flight, resulting in the loss of all 7 crew members. The subsequent investigation revealed profound vulnerabilities in the vehicle's solid rocket booster joints, exacerbated by freezing temperatures. It exposed a breakdown in NASA's communications and safety culture, where schedule pressures overrode engineering concerns. The loss of Challenger removed any remaining assumption that access to space had become routine. It was a stark reminder that launching a reusable, crewed spacecraft off the side of heavy-lift rocket engines remained a highly dangerous and experimental endeavor. When the program returned to flight, the shuttle matured into a highly specialized orbital repair ship. Using its 50-foot robotic manipulator system, the Canadarm, crews could grapple, deploy, and retrieve massive payloads directly from the cargo bay. In December 1993, the crew of the Endeavour captured the defective Hubble Space Telescope. Over a series of spacewalks, astronauts were able to utilize the robotic arm as a stable work platform to successfully repair the observatory's optics. The shuttle also became a vital tool for international diplomacy and construction. After a series of docking missions with the Russian space station Mir, the orbiters physically joined the first modules of the International Space Station, serving as the heavy lift vehicles that built the outpost piece by piece. But in February 2003, tragedy struck the fleet again. At the conclusion of STS-107, the Space Shuttle Columbia disintegrated in the upper atmosphere during its descent, claiming another 7 lives. The investigation traced the failure back to the launch itself. A piece of insulating foam had broken away from the external tank and struck the leading edge of Columbia's left wing, critically fracturing the fragile thermal protection system tiles designed to shield the aluminum airframe. The loss of Columbia cemented the dual reality of the shuttle. It possessed unmatched capabilities as a heavy construction platform, yet its design was inherently fragile, requiring thousands of hours of meticulous maintenance between every flight to ensure the integrity of its heat shield. On July 8, 2011, Atlantis lifted off for the program's 135th and final mission. Designated STS-135, its primary objective was delivering the Rafaela logistics module to the International Space Station. To conclude a mission and initiate the return sequence, the orbiter executes a precise maneuver. It physically flips to fly backward, firing its orbital maneuvering system engines against the direction of travel. This deorbit burn slows the vehicle just enough to drop its trajectory into the Earth's upper atmosphere. To dissipate its tremendous orbital velocity, the vehicle enters the atmosphere at a high angle of attack. The resulting compression creates a sheath of plasma around the belly of the craft, subjecting the thermal protection system tiles to temperatures reaching nearly 3,000 degrees Fahrenheit. Plunging toward the runway, the orbiter manages its descent profile by executing a series of wide banking maneuvers known as S-turns. By rolling left and right, the spacecraft bleeds off excess speed and altitude while maintaining a precise glide path. The final touchdown occurred on July 21, 2011. Bringing a 100-ton glider onto a runway required exact calculations from the crew. Without engines to abort a landing or correct an undershoot, they had only one chance to align the vehicle and drop the landing gear. The Space Shuttle never realized its original promise of cheap, routine spaceflight. Instead, its legacy lies in its sheer capability. Over 30 years, the world's first multi-role spaceplane redefined how humanity could live, construct, and conduct science in the hostile environment of low Earth orbit.